want to, because this is so important, so I rushed through things at the end of lecture on Monday, right? I want to calculate the energy of an electric field distribution. So we call for a thin spherical shell of radius R0, right? Where you have a uniform surface charge density sigma given by Q over 4 pi R0 squared. The electric field right outside of the shell, I call it E plus, right, is given by sigma over epsilon naught. And the electric field inside is just identically zero by Gauss law, right? This is all by Gauss law. And the electric field is, of course, radial in this case. That's the only unique direction defined. And I didn't exactly do this, but the force at the surface, suppose I put a differential charge dq here, or if I just cut out, a small part of the shell, right, of area dA, right, where dq is sigma dA, right, then the force on that cut out little patch will be just the average of the electric field outside and inside, okay, times this is just the electric field times dq, right? I'm not going to prove that. You should go to the proof. It's pretty. It's not that involved, but you know, it still takes some time, right? To show that what you have is a factor of half here, okay? So the force is given by half of sigma over epsilon naught times dq, right? So this force is repulsive. It tends, if this is made from balloon, right, from rubber, then it would tend to like stretch out, okay? And if you want to squeeze the shell to a smaller size, then you have to work on it. You have to apply a negative force on the shell, right? And that force has to counteract this force at the surface of the charge, okay? And the total force is just half sigma over epsilon naught, okay, times the total charge at the surface, right? Total Q. And total Q is just, in this case here, this is the area of the shell times sigma, okay? So, where was I? So, if you want to squeeze this to a smaller size, then you have to do work, right? And the work done to squeeze the shell from radius R0 to R0 minus GR, right, is given by dW. It's a positive work because you have to actually work against the Coulomb force, right? And you know from mechanics, dW is just force times dr, right? Okay, so substituting the value of the force from here, you get half sigma over epsilon naught times 4 pi R0 squared dr. I'm just including sigma here, okay? And just brings out some algebra, you get this result here. W is half epsilon naught, and then sigma over epsilon naught is just E squared, okay? This is the field right at the surface of the shell, okay? Times 4 pi R0 squared dr. And this is just a differential volume. This is exactly the new volume that you create. Okay? By squeezing the shell, right? So before you squeeze the shell, the electric field in this volume here is zero, right? Right, because the charge is just outside, it's just outside of it, right? After you squeeze it, you get electric field, right? Suddenly, after you squeeze it, there is electric field here, right? It becomes fine, right? And it's given by sigma over epsilon naught. Okay, so you can do a different way of accounting in this case. You know that the energy gain by the system is just the work applied, right? This is energy gain. In this case, it's electrical. is equal to the work that you do, right? Right? And by this equation, it looks like, it's equal to half epsilon naught times the electric field squared times the new volume that is created. Okay? So, and I can do this, from all the way from, say, from infinity all the way to some radius r, right? And you can generalize this statement by saying, well, maybe I can also write it this way, right? That the energy, the total energy of a system is just an integral of 1/2 epsilon naught times the electric field everywhere, and then you just integrate over the volume. Okay. Is this clear so far? This is a new way of accounting. This is a new way of measuring electrical energy. So as you know, I'm not exactly deriving this. I'm just motivating this, right, from that kind of consideration. But you can derive this also from just Coulomb's law. Okay. So let's use this to calculate. In this case here, we're using this new way of calculating energy to calculate an energy of a spherical shell, right? Recall from the past week or so, we actually did a calculation of an energy of a spherical sphere, right? Of radius r equal of radius a, and you find that the energy is equal to, remember this is using Coulomb's law by looking at the interaction between charges, right? You get the 3/5 times, for a uniform sphere, 3/5 of times 1/4 pi epsilon naught q over a, right? You remember this? Okay. But we haven't done, say, calculating the energy of a spherical shell. If you want to use the same method, like method of Coulomb's force, it's not that simple, right? Because you have to integrate over a sphere, or over a shell, and as you know from yesterday, that kind of thing is difficult, right? Yesterday we had a discussion, right? Yes, but it turns out it's easier using this method. So for a spherical shell, you know that the electric field, I'm just repeating this over and over again, the electric field is 0 inside, outside is 1/4 pi epsilon naught q over r squared, right? So you have electric field everywhere. And I just want to integrate over each square, all over space, right? And that's the integral. This is the expression for the energy. U is half epsilon naught, okay? An integral from, only from a to infinity, right? Because the electric field is 0 inside of a sphere of radius a, right? So a to infinity of the electric field squared. I guess I made a mistake, right? This is square, right? Okay. So what you have then becomes so one power of the 4 pi cancel that 4 pi, right? And then there is this power of epsilon naught cancel 1 power of the epsilon naught over here. So you're left with 1/2 1 over 4 pi epsilon naught, okay, q squared, okay, an integral from a to infinity, 1 over r4, r squared q. And this the integrand then is just 1 over r squared. If you do the math correctly, you'll find that the answer is 1/2 1 over 4 pi epsilon naught q squared over a. That's the energy for making a shell with the just uniform surface density sigma equal q over 4 pi a squared, right? That the energy to assemble that is given by this expression thing.
On the board of book, can you go over how you guys see this story?
Where? Here? Here, right? Yeah. This comes from the force here. The force at the surface of the shell is given by this expression, right? This is clear except for the factor of 1/2 that you should learn to do, okay? And then sig dq is just the total charge on the shell, right? So you have 1/2 sigma over epsilon naught times 4 pi r naught square sigma. So that's why you have the sigma squared, right? That's sigma squared. Okay? Other question? So this is the expression for the energy. Okay? Let me erase this part. If it takes for the same amount of charge and the same radius A, right? It takes less energy to assemble a shell. To assemble a shell of such Q, this is just half 1 over 4 pi epsilon naught Q over A. But to make it into a uniform sphere, you get d-fifth, just to make it equal, right? Denominator 1 over 4 pi epsilon naught. Is that right? Q over A. And this is 510. Is that correct? Okay. So what happened is that from infinity, if you take this charge from infinity to assemble something like this, you have that, right? But once you achieve this, right, if you want to make it into a uniform sphere, right, you sort of kind of smear out these charges inside, right? And you need to work also to do that, right? So the amount of work to get from here to here, you have to add another 1 diagonal. Is that right? And then 4 pi epsilon naught. Okay. This is the extra amount of work that you need to do to actually create that, right? You can also think of it as the energy it takes to create all the field inside here, right? Because all the field inside is a steam not. And try to do this at home, right? If you integrate integrate electric field all over the inside of the sphere, you should get that. Okay. Is that clear? Yes. So.
Why is there a squared on the Q in U here, but not
yes.
anywhere else?
If I make a mistake somewhere, it should be Q, just Q, right? Yeah. So why is it Q squared? Yeah, it should be Q squared, sorry. Right? If I make a mistake, Q squared. Yes. Did I square everything already? Yes.
So are you saying there that like if you're taking this sphere and you're like making it bigger, then because you're creating a field, then it costs energy?
Yeah, if you make it bigger, are you talking about the shell? It's easier to think about the shell because it's binary. Inside is 0, outside is finite, right?
Mm-hmm.
If you squeeze it, right, then you're creating a new volume, right? With electric field, where previously it's 0.
Right. In the case of the filled sphere that you're talking about,
Yes,
Because like you just said, it's linear, right? So if you make it bigger, then aren't you increasing the field, or?
If you make it bigger, you actually lose its energy, right? Because what happens is the field inside is that right? I don't know anything about this. So this goes as like that, right? And then you're saying that if I make it bigger, right? Then it becomes linear and then it drops. You have to be counting right. I don't want to make a mistake. Like last time, I think Charlie proved that. I'll talk about it in discussion on the shape of that electric field inside the big spherical shell. But the simplest thing to see it is that example on a thin spherical shell, where the field is inside is zero and finite outside, right? You squeeze it, suddenly you acquire a new volume of electric field. Okay? And to do that, require an extra amount of energy to create. Right? And that extra is given by half epsilon naught E squared times the volume. Right? So that motivates that expression. I mean, we didn't derive it exactly, right? That motivates this expression that the total energy of a configuration, total energy of a configuration of charge is just given by the integral over all space, right, of the electric field squared. Okay, and we use this to calculate the energy it takes to create this configuration of charge, right? And it's given by that. Okay, so previously, let me erase this part. Let me erase this part. Just briefly, we know in the past, if the energy of a configuration of charge is given by, if I have a collection of charges, just to make it easier to write, if it's discrete, then the energy is given by sum over I to the 1 to n, Qi Qj over Rij, right? Where Rij is the difference, the distance between these two charges, 1 over 4 pi epsilon naught. Okay, remember this part? Remember this argument here, right? Is this really equivalent to that? That's the question, right? Okay. So in particular, say if I have two charges, right, Q1 and Q2, right? Q1 creates electric field everywhere, right? As you already all know by now, the electric field is radially outward from a point charge, and then you have Q2, right? Okay, and so on. Okay. And because of the principle of superposition, the total electric field, right, is a vector here. It's just E1 plus E2, right? Okay. So let's try to calculate the energy of this configuration. Just two charges. Okay? Then the energy is given by 1/2 epsilon naught integral of E squared. E squared is the dot product into itself times dV. Right? So when I do that, I get the just squaring that expression here. I get 1/2 epsilon naught, right? An integral of E1 squared dV plus an integral of E2 squared dV, right? Where E1 squared is just E1 dot into itself, right? Okay. This is a dot product, by the way. Everybody's familiar with the dot product, right? Okay. Plus 1/2 epsilon naught times 2 integral over all space one, right? Okay. So there are three terms here in the formula. Oh, and it's a factor of 1.5 epsilon naught here. Okay. So there are three terms here. The first term is just say if I have elementary charges, right? We'll give an example of a proton and an ion, but just to be simple, let's consider this as a proton and an electron, right? Or maybe a proton and a proton. Okay. Then the first term and the second term, right? As you know from your study of a spherical shell or a spherical sphere, this is just the energy to assemble the charge, right? There is no interaction. By itself, this is what it takes to create, say, a proton, right? Or a positron, or whatever, right? And this is where there's a lot of problem, right? Because we discussed this in the past, that when you take a limit when a goes to 0, this term blows up, right? But you don't have to worry about it because this is always constant. The whole u is just u1 plus u2 plus 1 over half epsilon naught, or half epsilon naught integral of 2v1 v2, right? This term is the term that has to do with the interaction between charge 1 and charge 2, right? And if you do this correctly, right, and it's doable, I advise you to try to do it, right? Try to evaluate that for two protons that are separated by a distance r, you will get an answer that's equal to, that's proportional to p1 and p2 over the distance between the two. And as you know, energy, what matters in energy is always the change in energy, right? You can always subtract this out, right? You can always subtract the energy it takes to assemble the electron, right? Because you can never destroy it, right? It's always there, right? Unless you're just actually disturbing the structure of an electron, right? Then you don't have to worry about this new term, right? All you need to worry about is the interacting term, right? And this is just given by that. Question? Okay, so let's move on now. That's all I have to say about electrical energy for a while. That's the end of chapter 1. Let's move on to chapter 2. Where we define the concept of electrical potential, right? Okay. So you guys are all familiar with the concept of electrical potential, or is this new? Okay. So let's motivate this by discussing work done against Coulomb force. Okay. Since you're doing work against the Coulomb force, it's given by integral of Coulomb ds. Okay, so so there is a charge here Q, right? If I take let's call this a capital Q, right? If I take say Q naught, right, from distance say r, let's put a Q naught here for now, right? Distance r1, and I take take it all the way to a distance R2 away from Q, right? Then the work that you do against the Coulomb force, in this case actually, the Coulomb force is in that direction, right? So you don't have to do any work, but the minus sign will take care of itself at some point. The work done is just that is this, okay? And in particular, because you know that Coulomb's law is given by 1 over 4 pi epsilon naught Q naught over R squared, right? This becomes an integral minus an integral from R1 to R2. Right? I'm just taking the path radial, just for simplicity. Right? This is the path C. Okay. C from R1 to R2, 1 over 4 pi epsilon naught Q naught over R squared, okay? And then do the math, you get this is equal to 1 over 4 pi epsilon naught Q naught 1 over R2 minus 1 over R1. Okay. So that work done, that you do, right, is that is equal to the, just like in your study of gravity, right? It's just the or mechanical energy that you did inside A. This is just an energy at 2 minus an energy, potential energy at 1. Okay? Okay? So in particular, if I take this problem again, right, and I take a charge Q naught from infinity, right, and I bring it to a point R, distance R near Q, then the work that you do from this expression, I'm doing things fast here, but I have it in my notes, so I'm not making any mistake. Then this expression is correct, and the work is just 1 over 4 pi epsilon naught Q naught 1 over R minus 1 over infinity, okay? And that is equal to U2 minus U1, right? Or UR minus U infinity, okay? Okay, so now with energy, you can always add or subtract a constant, right? You define that the energy at infinity, the potential energy at infinity, this is potential energy, by the way. Potential energy at infinity is 0, right? And this is also 0, right? So UR, then it's just 1 over 4 pi epsilon naught Q naught over R, right? Okay? And also, so there's nothing new there, you guys know all about that already. Also, another thing is we've been doing this path integral along a special path, right, radially, right? But because F Coulomb force is a central field, right? Meaning that the force is always radial. It's radial from point charge. Okay. Then that integral F Coulomb ds, right, from R1, R2, right, is actually independent of path. And I'm not going to prove it in this class or in lecture. Maybe we can do it in discussion, but it's also discussed in your math book for central field. It's also discussed in Purcell. It's not that difficult if you go through it. So an equivalent statement of this is that this integral of f Coulomb ds is equal to 0, right? These two statements are the same, right? If this is independent of path, then closed loop integral of f ds is 0. Okay? So now, by analogy, let's look into an integral, the path integral of electric field, right? Now we know that electric field at any point in space, right, is just the force. If I have a charge Q naught, right, then if I find the Coulomb force on that charge and I divide by Q naught at that particular point, that can be the electric field. So basically, the structure of the electric field looks very similar to the structure of the Coulomb force. So in particular, this integral E ds from R1 to R2, okay, is also independent of time. Right? Okay. So if I have an electric field, at some I didn't do this, but you can also draw electrical field lines. So if I have charge distribution, or just for simplicity, let's just have one charge. You can have an electric field pointing all radially, right? And it means that's 1 over r squared away from charge, right? And you can connect all the tangent line and form the electric field lines. Right? Okay, so if I have two of them, Q1, you do this and convince yourself or do it on Mathematica or something. If this is Q1 and Q2, suppose Q2 is actually negative, then your electrical field line, will look like this, right? What you do first is you draw all these electric field lines here. It's inward here for the minus charge, right? And then you just connect along the tangent line, you'll get something like that. Okay. I can do this because I'm not very good at drawing, but you get the idea, and there's a long discussion in Purcell. And basically, if I have ones like that, if I take any path, right, any path, C, that integral is always equal to 0 for electrostatic conformation, right? Okay, only for electrostatic. If the charges are stationary, this is always true. Okay, so this is the fastest I've come to. Let me take a look. Any questions so far?
Yes, sir. Participants, now let's do like complex analysis on the system.
This expression allows you to do complex analysis on a system.
Yeah. Because then you can do the loop, right?
I mean, you have to do some kind of a continuation to a complex plane first. It's not like clear to me how you do, what's the necessity of doing that for this particular problem. Maybe there's, for some problem. Maybe.
I was just wondering because it's like the condition, isn't it?
Yeah, it's similar. It's similar to the, no, it's not the same here. This is much simpler. It's not the Cauchy-Riemann condition. Right? Anyway, I have a question. Okay, so in particular, we find now, because of that, because we've been doing this many times, right? Anytime you have path independent integral, right, you can always define a state function, right? R1, R2, right? Minus sign is to conform with the original definition of work done, right? Because you're doing work against Coulomb force, right? So I want to identify or connect the concept of potential to potential energy, right? So I want to keep the minus sign. It's not necessary, it's up to you, right? And this is just, what shall I call it? Phi 2, 1, okay? And say if I have a point charge Q1, or why is it Q1? Am I not Q1? But just Q, right? Positive Q, then if I do this integral from R1 to R2, right? E21 is equal to minus ER, right? I'm taking it along the radial direction, and I know the answer is independent of path, okay? And this becomes, if you do the integral correctly, this becomes 1 over 4 pi epsilon naught Q, right? If you charge Q, 1 over R2 minus 1 over R1, okay? So the integral here, which is equal to some difference because it's state function, and let's call the state function V. This is just V at 2 minus V at 1. Okay? So in particular, if I take the situation where R1 is from infinity, right? R1 is infinity, okay, and I bring it all the way to, I suppose R2, let's call R2 equal to R, right? Then this becomes, this integral becomes a Q over 4 pi epsilon naught, right? Any questions so far? I'm facing this direction all the time, right? 1 over R minus 1 over infinity, right? Because R2 is R, R1 is at infinity, right? This becomes V2 minus V1, right? Same thing with the state function. I can always add and subtract a constant, right? And let's define V at infinity equal to 0, just like in the concept of potential energy, right? Then this also goes to 0, right? So the potential at R, okay, due to a point charge Q at origin, right, is given by Q over 4 pi epsilon naught 1 over R. Okay, and this potential looks like this. And that's 1 over R. Okay. Any questions so far? We'll talk about, let's continue. So just remember that, right, for point charge. Now, what happens if I have a distribution of charges? Right? if I have a density of charges distributed in space, right? You know, by principle of superposition, right? Because electric field at, then the potential at, let's call it, let's define the origin over here, let's call this point R. Let's use R prime for this, right? Then the potential at R is just equal to summing all the potential coming from each differential volume, right? Okay, and it's just 1 over 4 pi epsilon naught, integral of rho R prime, dv prime, right? This is just the differential charge divided by R minus R prime. Okay, because this distance here, this is R prime, and that distance, this is R minus R prime. Okay, and what we want is just the distance between the 2 points, and then you integrate. This is for just. So it's very simple, right? It's just scalar. There is no factor here, right? This is the density of charges in that distribution, and this is just the distance between the point of interest and the differential volume. Okay, and then you integrate. Okay, so if you recall from yesterday, right, we tried to solve some of this problem of finding electric field for line charts or I don't know, what did we do yesterday? This charge of finding the electric field coming from this. And there's all this projection that we have to do in the end. You know, I did a bad job, I didn't solve it, it's complicated. But for potential, it's easy because it's not a vector, you don't have to do any projection, right? So that's part of the attraction, is if you're interested in calculating something. So let's try to go by doing what's the unit of potential? So if I just look at unit, the unit of potential is basically the unit of energy divided by the unit of charge, right? Right? Because if I use Coulomb force and I do a line integral, I get energy, right? And if I use electric field and I do a line integral, I get potential, right? And the relationship between Coulomb force and electric field is just 1 over charge, right? So the unit of potential is just joule per coulomb, right? And this is defined to be called Coulomb. It has a name. Oh, it's right.
Yeah, I mean, like,
Oh, but yeah, I guess I know. Yeah, that's right. It's 1 volt. Yeah, and then what? 2 volts.
yeah.
Okay. Yeah. That's the unit. Okay. Let's do an example. Right. Simplest example is, I suppose, this is given in the book. Any questions so far? Okay, let's do an example. Well, there's an example that's given with a line of charge, right? Line of charge from -infinity to infinity, right? With the line charge density. Lambda, right? And we know that the electric field has to be radial here. We know that this is equal to lambda over 2 pi epsilon naught r in the radial direction, right? we want to find the potential difference everywhere, right? Say at point R. Okay? Now in this case here, right, recall that I've been defining a potential at infinity to be 0, right? In this case, it's not possible to do that. You cannot make this equal to 0, because what happened is this line of charge goes all the way from minus infinity to infinity, right? So the potential at infinity actually, it goes up at some point. The only thing you can do is define a reference point somewhere else, and it doesn't matter where, right? So let's just evaluate something. Let's evaluate this integral. Right? R from R0 to R, right? And this is just phi at R minus phi at R0, right? Okay? And I'm just doing this integral radially. As you know, it's independent of path, right? Just take 2 points, R0 and R, and I'm just connecting it radially outward. Okay? And when I do that, I get an integral of minus lambda over 2 pi epsilon naught, integral from R0 to R, 1 over R to R, right? And when I do that, this becomes lambda over 2 pi epsilon naught, 1 over R minus 2. What is this integral here? You know, the value of this integral is, I guess I still keep the minus sign because this is just 1 power of R, right? So it's log R minus log R naught. Okay? So the potential at R minus the potential at R naught is given by lambda over 2 pi epsilon naught log R naught minus log R. Okay? And I'm just looking for the spatial dependence of the potential. So this is a constant, right? This part is also a constant. I can just lump them together and forget about it, right? This becomes then minus lambda over 2 pi epsilon naught log R plus constant. Okay? So if I throw it, potential at R, the function goes like this, right? It's minus log R. Okay? This is one example. I don't have time to do another example. We can do it for a surface charge of this. But next time on Friday, we'll go in the other direction, right? From electric field, if you do a line integral of electric field, you get voltage, potential difference, and you go the other way, right? If I know the potential difference, right, in the end, what is basically important for us is measuring the electric field. So knowing the potential, how can we evaluate the electric field? That's what we'll do next time. And midterm is at 5. We'll start at 5:10. But come here at 5, so that we can all get settled down. In this room, 5 o'clock. Start at 5:10. Bring a sheet of paper. We will go.